Hey everyone, my name is Naminan and I'm a PhD student at KAIST-AI. Today I'm excited to present our work that has been accepted to CVPR 2026, Interpretable Debiasing of Vision Language Models for Social Fairness, a collaborative project done between KAIST, the University of Copenhagen, and NVIDIA. Vision language models inherit severe demographic biases from their large-scale training data. For example, CLIP exhibits a highly skewed gender distribution when retrieving images for a CEO, while large vision language models like Interpretable provide definitive biased answers to highly ambiguous questions. To address this without significantly changing the model, we introduced Debiased Lens. It selectively mitigates social biases across both image and text encoders while preserving original downstream performance. Existing postdoc or test-time debiasing methods only treat surface-level symptoms. They fail because individual model neurons are highly polysemantic, meaning that they are entangled with semantic knowledge with social traits. By attaching a sparse autoencoder or SAE to the VLM encoders, we observe that the feature space could be disentangled. This allows us to isolate monosemantic social neurons that track traits like gender, age, and race, without requiring demographic labels during training. Our debiased lens framework operates in three modular stages. First, an SAE is trained on the final layer of a frozen VLM encoder using a reconstruction and sparsity loss. Second, we probe the trained layer to actively localize social neurons. Third, during downstream inference, these targeted biased neurons are deactivated, yielding clean debiased representations. Let's look closer at the identification stage. We evaluate each hidden neuron based on its consistency and specificity across demographic groups. We extract effective neuron sets by setting a strict activation threshold tau. By applying a set difference operation, we isolate attribute-specific neurons, N sub G, that respond uniquely to a target group. The neuron with the maximum mean activation value is selected for neutralization. During the final inference phase, the identified bias components in the latent vector Z are set to 0. The decoder then maps this vector back into a bias-free reconstruction, V hat. Crucially, to prevent semantic distortion, we interpolate the reconstruction with the original hidden feature, V, using a controllable gating weight, alpha. This modified feature seamlessly replaces the hidden state for downstream operations. We evaluated our approach across standard CLIP variants on the Fairface dataset using multiple text prompt categories. Debiased Lens achieves a massive reduction in mask skew scores across adjectives, occupations, and stereotype prompts. Interestingly, text encoder modulation works exceptionally well on base models, whereas image encoder debiasing scales better with high image resolutions. When deployed on larger generative architectures like Lava and Interpretable, our method achieves an outstanding trade-off compared to traditional pruning or fine-tuning methods. It sharply decreases the gender disproportion rate with a near negligible drop in general perception capabilities. As shown in the bar chart, the probability gap between genders becomes statistically non-significant for almost all textual prompts. A core strength of our approach is its fine-grained neuron specificity. Modulating a tiny handful of gender neurons leaves age and racial bias scores completely untouched, and vice versa. Furthermore, as visualized on the right, the top activating images for our discovered neurons map directly to clean human interpretable concepts. To study how training data affects these social features, we curated custom synthetic datasets with and without background information named SBSyn and SBSyn crop. Probing reveals that utilizing facial focused datasets produces far sharper and cleaner social neurons. Impressively, the neurons isolated using the real-world Fairface dataset generalized to synthetic test environments. Our ablation study maps a clear Pareto trade-off governed by the weight parameter alpha. Setting alpha to 0 yields a baseline model, while alpha to 1 maximizes debiasing but degrades general breathing performance. Based on these empirical curves, we suggest a balanced default of alpha to be 0.6, allowing practitioners to easily tune the framework to their exact requirements. In summary, we introduced Debias Lens, a highly flexible model-agnostic debiasing framework. By shifting bias mitigation from opaque black box adjustments into targeted interpretable interventions, we believe this work marks a foundational step toward developing deeply trustworthy and socially responsible multimodal systems. Thank you for listening. Have a great day.